How many trig functions do you think I'm going to define? How many trig functions do you think that they made? Why do you say that? That answer is wrong, but for the best reason, I think. Why do you say 3? Oh, I see. Okay. What is it you guys created, though?
Ratio.
How many of those did you make?
6.
So let me ask you again. How many trig functions do you think we're going to work with? 6. Let me stop for a minute. And that's another reason why I'm this seems really silly, but it's so powerful at the same time. You guys made 6 ratios. Everybody did. If somebody would have forgotten one, somebody else would have been like, oh yeah, you forgot this. Now real quick, one reason why I thought you said 3 is, do you guys see 3 main ratios and the other ones do something? Like, there's a 5/13 here, yes? Isn't there also a 13/5? So aren't 3 of them just other ones turned over? So we're going to have 3 main trig functions, and then 3 trig functions that are just like, oh yeah, those guys are flipping. Yeah? That's the official, they're called reciprocal trig functions, because they just reciprocate. Okay. So, all that is left now is for us to define, for example, a name for the function that when I feed it an angle, it gives me the ratio, for example, of the vertical to the hypotenuse, right? The 24/26 that they got there. And so forth. I need 6 of them. So let's start with that one. Okay, so let me do this. Just to be able to capture everybody's triangle. And by the way, let me do this before I forget. Just so we don't forget today and how much fun we had with.
Look at that, it's fractions. They're all over the damn place.
Whee! And then we got them over there. Okay, I'll stop. So if you watch that part, you might get seasick. So if I just draw, I'm going to make this theta. Now, let me just lay down something very quickly. Has anyone ever heard of something called SOHCAHTOA? Okay. I have to be really careful how I say this, because what I normally say is SOHCAHTOA sucks, and I actually stand by that. If you learn SOHCAHTOA, it does a good job for what it's for. How much is it for? This much. So what I teach is something that goes forever. It goes into Calc 1, 2, 3, it goes into physics, it goes into everything. If you learn SOHCAHTOA, it very quickly loses its usefulness. If you don't know SOHCAHTOA, you're actually in a really good place. Okay. If you do know SOHCAHTOA, you're fine. If my angle is down here, so I can put my angle in the bottom, which side do you think I look at as the x side? Which side kind of matches up with our xy coordinates? Which side would you say is the x side? The bottom. You guys agree? Isn't that kind of like lined up with the x-axis? So as long as the angle is in the base, this x side, what side is this one? Because I want to know. And then what's the last side? Well, we'll call it, for right now, we'll call it H. Later, I might call it R, and I'll explain why. But let's call it H because it's the hypotenuse, correct? I need 6 trig functions. The purpose of the trig function is if I change the angle a little bit, the ratio is going to change. So that I would have an input of an angle, and it would spit out a decimal, which would be the angle, the ratio. You guys with me? Okay. So unfortunately, here's what we chose. Do you guys remember, well, hopefully you do, logarithms? And one of the worst things about them, I really hope you guys agree that they're nowhere near as hard as they first seem. They're just powers.
What power does this need?
That's all they are. But I think the thing that gets in the way for most students immediately is it's a freaking word. Yes? It's like, who put what? What? Who put words in my equation? What the shit? So here come more words. So we chose to represent the y over h ratio that you all made, we chose sine. I'll put above the full word. So yeah. Math is the root of all evil. Here's the sin that's inherent in the math. So for a given angle, if I made this angle bigger, what's the immediate thing that would happen that sine cares about? I need you to see this. If I made this angle bigger, yes, like this, yeah, and I kept h the same, what changes that sine cares about? What got bigger? Y got bigger, of course, yes. If I open my mouth wider, I can stick a bigger stick into it, yes? And I'm a big geek. I'm like, just tolerate me. I'm a big geek, so I think about Return of the Jedi when Luke puts the freaking thing in the Rancor's mouth. I don't know, have you guys ever seen that movie? Mm-hmm. And you're all like, yeah. Several of you look at me like, I'm sorry. So I think of angles like how big a mouth is, and that directly relates to how big of a stick, meaning how big the side is. So the biggest side in a triangle is going to be the one across from the biggest mouth. That's going to become very useful in a few different places. So if I change my angle, but I leave h alone, the output to the sine function changes. For every input, there's only one output. That's why I know they're going to exist. And we just created this. We just made it. And then, for the ratio x over h, we use cosine. Now, so far that feels pretty good. Do you agree? You got sine as the y piece, and then cosine. Aw, that's what my grandma did when I got my first car. Cosine. All right, so that's two of them down. Thanks. That's the true story. Got my first car, and my grandma was like, I'll cosine on that loan. It's like, good, because I'm going to default. Okay. The third basic trig function. What's the last ratio that we haven't really made? Not one that's just reciprocal. I don't care about h over y and all that crap. What's the last ratio we haven't made at all yet?
X over.
Yeah, y over x or x over y. So let's do y over x. So the third basic trig function is called the tangent. And that is y over x. So those are the three basic trig functions. We will eventually be memorizing, for certain angles, we're going to memorize what the outputs are. And I'm actually going to prove to you why they are. That sounds good. The great thing is, the other three are just going to be turning those over. Now, let me start with the one that makes the most sense. If I flip the tangent over, that's cotangent. But now you see how we have what seems to be a naming problem. Sine and cosine are already there. So what is sine's reciprocal called? Well, let's start with cosines. What's the reciprocal of cosine? Well, it's obviously going to be secant. And I say that facetiously. Ain't nothing obvious about that shit. So the secant is the reciprocal of the cosine. Now, right there, you're like, and I got to memorize this? Yes, you have to memorize all this. And I'll show you what I did as a student when I first learned this. So what do you think? Do you see everything up there? Sine, cosine, tangent, cotangent, secant. What do you think sine's reciprocal function is? What's the only thing that's kind of missing? Cosecant. Cosecant theta is h over y. Do you see how I just flipped it? And this is cosecant. I've got a handout that's got all this on there also, so you can actually see it in computer writing instead of my writing, which is good. How are we doing so far? I desperately want you to understand it. This is almost the first place you guys are seeing functions being constructed from the ground up. We threw some triangles on the board. We played with some numbers. And we went, oh shit, look at that. I can make this function because there's, for every angle there's a certain side length. So therefore there's got to be a function I can make. And there we go. There's 6 of them to capture the 6 ratios that we made. So here's the crazy thing. We're going to do a shit ton of stuff with trig functions. It's going to be crazy the amount of stuff we can do. And you're going to lose touch with the fact that all trig functions are is ratios of sides of right triangles. That's all they are. Okay, how are we doing so far? Let me ask you this question. Of course, what's the longest side in that triangle? H. Can sine be bigger than 1? Which really means, can y ever be as big as h? Because what does h have to be? It has to be the biggest side in there. So neither one of the other 2 sides could equal it, correct? So tell me, what did we just sort of figure out, just physically? What's the biggest output sine could get? Maybe the biggest it could get is 1, or maybe it can't get up to 1. Are you guys with me? But it definitely can't have outputs bigger than 1. You guys with me? All right, I just wanted to say that just because I realized, oh yeah, you can actually get that physically from here. We'll go deeper into that later. I just want to lay the groundwork. Okay. Now, what I like to do right after doing something like this is to actually get into a concrete angle and figure out some stuff about it. By the way, before I forget, I'm doing section 7.2 in the book before I do 7.1 because I think it makes more sense. Well, we'll see if you agree. So this is all coming from section 7.2. Oh, wait a minute. I don't have to go to, oh, hold on. I got a handout. This kicks ass. There it is. Yeah, all right. This is a little silly. Well, it's not that silly. The first 2 questions should be pretty, oh, this is just for you. That's for you. First 2 questions, the answers are surrounding you, but now we can look at it kind of the reverse. So there's 2 things going on this handout, by the way. What letter did I use for the angle in these problems? A. A. So in general, we either use theta, we can also use some other Greek letters, or we use capital letters. And later today or next week, you'll see why. So here's all the definitions. I forgot that on this handout, I put R here instead of H. Let me see, real quick, just to show you why that is. Here's a circle, kids. Pretend like that's a circle. And let me put X, Y there, so the center is 0, 0, yes? Let's pick a point on the circle. And this point is X, Y, is that cool? So what is this distance here? Don't overthink it. What does that have to be? It has to be X. And what does this have to be? Y. So if I do this, do you see how there's a triangle in that circle? No? Yes? Do you guys see how there's a triangle in the circle? In fact, it's a right triangle. So all this trig shit we're doing is going to work. This is the unit circle, basically, if I made the... But before I even talk about unit circle and all that kind of crap, what is this geometrically? I love it. Trent, I knew I was going to look at you and be like... You almost are right, though. It's a line segment. Thanks for playing. That line segment, since it's in the circle in a certain orientation, what is it also known as? I think you just said it. The radius, yes? So that's why instead of calling it hypotenuse, we might sometimes call this R for radius. So that's why I've got R's here in this one. So it's either R or H. They both mean the biggest side of the triangle. So go ahead, and you've already got answers for this first one, but it's nice to kind of do the same work, but just backwards, the different way from what we did. What do you have to be careful about in part B? In fact, here, before I unleash you on this handout, what if I had, let me see, well, I'm just going to make up, no, Jeff. Sure, we'll do 6, 8, 10. All right, yeah, let's do this. B. If I wanted to know what the cosine of B was, and I know we just learned it, but you can reference your notes, you can reference the worksheet. What ratio does cosine B want me to make? What ratio does cosine B need? Look at your notes, look at the sheet. What does cosine B need? What is cosine B defined to be? I mean, what's cosine of theta? Cosine of any angle. Sorry. Yes. X over R or H, yes. Why do you have to be careful the way the triangle is? Because what side is the X side? And I'll tell you it is an 8. Why not? Where's the angle we're talking about? Is it in the bottom of the triangle? So, SOHCAHTOA, if you know it, doesn't need me to turn the triangle. So the one thing that the way I teach it that you have to do sometimes is you have to turn the triangle. So what's the X side? 6. And what's the Y side? 8. And of course that's the hypotenuse, we'll call it R. So then what would cosine B be? 6 over 10, which reduces to 3/5. Yay! You guys with me? So on the first problem, it's nice because I gave you the angle on the base. In the second problem, you just have to turn it first. All right, go for it. Once you've got all 3 sides of the triangle, and my angle is in the base, so that's my y, that's my x, like it should be. Sine of the angle is defined to be the y over the hypotenuse. Now, I'm going to go one more step right now, and I was curious if anybody has done this before, remember this. Radicals, do you all agree that radicals kind of suck a bit? Square root of 4 is nice, but square root of 5 sucks. Yes? That decimal is just crazy, it just goes forever. So not only is it bad to have a radical kind of hanging around, it is so much worse to be dividing by a radical. So there is a process we use, it's called rationalization. It's not the same idea as in psychology, but I want to make the bottom become a whole number. Now here, this is going to sound silly for a bit. Why can I do the square root of 9, but I cannot do the square root of 3? Why? What is 9 made of? How many? 2 3s. And what does the square root need in it to be able to be done? 2 of something, yes? So if you really think about it, I don't think I've ever said it that way, but that's what it's for. Square root of 49 works because 49 has 2 7s in it. Square root of 47 doesn't work. 47 ain't got nothing nice in it. Yes, poor little dude. So, why can I not do the square root of 41? Because how many 41s are in there? How many 41s are in here? Don't overthink it. There's 1, yes? So what do I have to give it so it's able to be done? No, you're not allowed to square the top and bottom of a fraction. It becomes something totally different. You can only multiply divide at the bottom and top of the fraction. So, watch this. If I multiply, because that's what I'm allowed to do,
I'm allowed to multiply or divide top and bottom. I multiplied by another square root of 41. Why is that legal? Because what did I just multiply by? 1. So of course it's legal. I can multiply whatever the shit I want to by 1. Yes? But what happens on the bottom? And here's a, so don't do 41 times 41 and get this big ass number. Half of 41 times half of 41 makes a whole 41. Do you guys see that? Or you can do square root of 41 squared is 41 because the square root and the square cancel. Do you guys see that? So I like this idea of here's square root of 41. Oh, here's the other square root of 41. It makes a whole 41, yes? So if I said, what's the square root of 11.8 times the square root of 11.8? It's 11.8. Done. Next problem, math boy. All right. So this becomes 5 rad 41 over 41. Now, if you didn't do that on this paper, you're fine. But you're going to have to do this everywhere. Everywhere. Whenever you have a ratio and the bottom is a radical, you got to rationalize it. You got to do this kind of thing. So thinking with that in mind, what's cosine A start off as? Yeah, 4 over square root of 41. Can anyone see what that would become if we did this here to it? Yeah, let's do it. Yeah, 4 square root of 41 over 41. Cool. Now, believe it or not, that's much preferred to a decimal. Because like I said, you have to stop writing the decimal at some point, in which case you are wrong. Because it don't stop there. So that's why we write it like this, because it's a more compact form that doesn't have to be rounded at all. That's just what it is. What's tangent? Tangent's the real MVP in this triangle. What's tangent? 5 over 4. Thank you, tangent. Now what's cosecant? If I had more room, I'd do it, but I'm the king of no room. Now here's the trick. And this is why I was kind of happy that not a lot of you guys did this. Don't flip this. Flip that. This is equal to this, yes? So what's the cosecant? How does it relate to sine? How does cosecant relate to sine? Yes, and here's how I remembered it as a student. And this is the best I could do. So if anybody comes up with something better, let me know. S goes to C. C goes to S. So sine goes to cosecant, cosine goes to secant. Admittedly not the best, but oh well. What do you want from me? Okay. If I build a time machine, I'll go back in time and we'll name it something better, but we can't do it. So what's the cosecant going to be? Square root of 41 over 5. What's the secant? Square root of 41 over 4. And then what's the cotangent? 4 over 5. Thank you. Yeah. So once you got the triangle fully defined, all the sides, the 6 trig functions just making the right ratio. So sine likes y, cosine likes the other guy. That's what I can do for you. This other triangle is much more straightforward, yes. The only thing I gotta be careful about is my angle is in the wrong place. So if I just take a second to do this, and I say, oh, that's y, and that's x, there, that's all I gotta do. If you know SOHCAHTOA, you don't have to do that, but was that hard to do? No. So what is the sine of A in this triangle? 5 over 13. So let's do the reciprocal at the same time. What's cosecant? 13 over 5. Cosine. What would cosine be? We already got 5, because that's the y side, yes? So cosine will be 12 over 13. So what's secant? 13 over 12. And then what's tangent? 5 over 12. And what's cotangent? 12 over 5. Okay, I like it. Now, listen, I want to address something right now. These are the tools. We're getting used to what the tools do. This is like first day you never touched a damn tool in your life and you give them a screwdriver. What's the first thing you do? You don't put together an entire IKEA thing. No. You just mess with some of you, like when they get used to what the weight is of this thing. They get used to what screws this works in. All right, so it would be awesome if you guys got to the point where you're like, okay, this is kind of silly. These just relate to ratios. Great. That's a beautiful place to be. I'm going to show you in a minute. I'll show you a physical, real world, immediate example of this that we can use. Something they do in the real world. Okay, because we're not where I don't know where we are. Did anyone try number 2? This is number 2 is this backwards. Number 1, I gave you a triangle, you made the trig functions. Number 2, I gave you a trig function. Now, what is a representative triangle this could come from? Here's theta. I'm going to put in the base for myself. If tangent is 2 over 7, what's one triangle that could have come from? Where would 2 be? Where would 7 be? Because we know what tangent is, yes? Do you guys see how this is like number 1 backwards? Yeah.
I was just going to say 7 is x and 2 is y.
Yes, because tangent's y over x. And since I was nice and I put the angle in the base for myself, tangent is y over x. What do I need to be able to figure out the cosine? Am I missing anything? I gotta use old Greek, dude, because I'm missing the last hypotenuse, because cosine needs... What does cosine need? The x side over the hypotenuse line. Do you guys, I need you to be with me. So this, do you guys see how number 2 is number 1 backwards? Number 2, I gave you the ratio, so you can construct a triangle. Number 1, I gave you a triangle, so you can construct the ratios. Yes? So most of the math goes both ways. We could all be jealous. How do I get, so what's Old Greek 2 say about this? I call it C. How do I set it up? 2 squared plus 7 squared, c squared, so I get 4 plus 49, and c squared, so I get c is square root of 53. And then what's cosine? Is anyone able to see where this is going to go if I apply that process? Because the same thing basically always happens. The top just picks up the bottom, and the bottom becomes a whole one of it. That is one way to say that. Does anyone think they got number 3 done correctly? Got it? What'd you do?
So cosine squared, you would just square x. It would be x squared over r squared.
Kick ass. Cosine is x over r, so cosine squared. And by the way, I always forget to point out, this takes more writing than this does. So these mean the same thing. We just decided to put the 2 there so we don't have to put the dumb parentheses. And real quick, do you guys see how this is a completely different thing? Here I'm squaring the angle. Here I'm squaring the cosine. So we said, I don't want to have to draw those dumb parentheses because I'm a lazy mathematician. Let me put the 2 there. Is everybody with me? I always forget, because I look at that and I know exactly what it means, but I'm like, some of you guys have never seen this shit before. That's what they mean when they put a little 2 in the middle. They're squaring the cosine. So cosine is x over r, so cosine squared is x squared over r squared. What's sine squared?
Y squared over r squared.
That's insane. Do they have the same denominator? Denominator. Yes. So I could do x squared plus y squared over r squared. Now, if you remember the triangle this is coming from, what is x squared plus y squared?
A squared plus b squared.
Yeah, so x squared plus y squared equals? So I can replace this with?
R squared.
So I get 1. So that's neat. It doesn't matter what angle it is. Sine squared of an angle plus cosine squared of the same angle is always 1. That's going to be really useful. Eventually. And then finally, one number 4. What does equilateral triangle mean? What is equilateral? Did anybody work out? You work out your lats? No. Or are you interested in lateral dorsal fins, lateral or lateral, whatever the shit, on the fish? I really know my marine biology is showing off. Equilateral means what? Sorry. Anyway, what did you guys draw? Did anybody draw the triangle? Do you guys remember what that is? It's not isosceles, it's not scalene, it's not right. What does equilateral mean? What are your lats? 3 equal sides. Because it's equa meaning equal, lateral is sides. So equal sides. If all the sticks are the same size, what's got to be true about all the angles? And if they're all equal, there's 3 of them, and they have to add up to be 180. Then each of them has to be 60. Now, can somebody tell me how long the sides are? And the correct answer is, I don't know. I don't know. Do the sides have to be any certain length? No, I don't know. So I want to do this for every equilateral triangle in existence. So how long is this side? X, kick X. So in algebra, the trick with algebra is if you don't know it, pretend like you do. Call it X. So I know exactly how long this side is. It's X. If this side is X, how long is this side? Holy shit, do it this side? Holy shit, okay. Now, everything we've done so far today involves what kind of triangles? Right triangles. Is this a right triangle? Damn. So I can't do shit. How do I have a right triangle suddenly show up?
You can cut it in half times.
Yeah, I can cut it in half any way, but I'm going to cut it like this. Then I make a right triangle, yes?
Yep.
I'm going to draw this guy. This guy I'm going to leave. Too bad. Too bad. I'm going to take this guy, draw him over here by himself. How long is this?
X.
X. How big is this? 60. How big is this considering I cut it in half? 30. And of course this is the 90 that we made when we dropped the height. Yes? So everybody with me?
Yes.
So very often in a problem, it looks like there's no right triangles, but you can find them. In fact, later this semester we're going to have a lot of fun with this crazy big ass thing we're going to make. And we're going to be finding right triangles in all kinds of weird places. Sounds right. Here's the issue. If I want to know, for example, the sine of 60 degrees. So I'm finally going to show you an input and an output for this damn function. Yes? When I input 60 degrees, Math Boy told me it better give me the same answer. There's got to be a number answer. We're going to prove what the shit it is. What's wrong if I want to figure out sine of 60 degrees? What do I not know? What does sine need? Is 60 in the base? Is 60 in the bottom?
Yeah.
Yes. So this is the y side. This is the and we're okay with this being called x. We're fine. That's still the hypotenuse. You guys with me? So what does sine need me to know? Needs me to know this. Yes. Why can't I figure that out?
You know the other side.
I only have one side. Okay. So how big, of course, is this side? This is the one thing we can figure out.
1/2 X.
It's got to be 1/2 x because I cut the damn thing in half, right? This is getting exciting. How do I want to write that? I'll just write it like that. Okay. Now this is where students kind of trip out. You're like, come on, jackass, why can't you give me some numbers? Too bad. Can you set up old Greek dude to figure out the height? I'll call it h. Why not? No, I won't call it h because it might be hypotenuse. I'll call it a.
1/2 X.
This is where you just brute force it. The process doesn't give a shit what the sides are. If it's a right triangle, the process works. So we're the humans. We care that there's not that many numbers, but I just plug shit in. Try to set up the Pythagorean theorem for this right triangle. You can do it. Just set it up. So the first level of Pythagorean theorem is just very straightforward. It's just that side squared plus this side squared equals that side squared, yes? So just setting the damn thing up is not hard. It's as you're doing that, you're thinking about what you have to do next, yes? But there it is set up. What is 1/2 x squared? 1/4 x squared. How do I solve for a? Yes, so to get a squared by itself, I subtract 1/4 x squared from both sides. That looks weird, but what is a whole thing minus a quarter of a thing? That's what that says. A whole x squared minus a quarter of an x squared is what? What's a whole minus a quarter?
3/4.
3/4. Yes, a dollar minus a quarter is 3/4. So this will be 3/4 x squared. By the way, this is nothing you ever have to do yourself. I might put a bonus problem or something. Yes?
Why does 1/2 become 1/4?
It doesn't. 1/2 squared becomes 1/4. What's 1 squared? 1. What's 2 squared?
Are you just moving the 2 to the back?
No, no. What am I squaring?
1/2 x squared.
I'm squaring 1/2 and I'm squaring x.
Okay.
1/2 times 1/2 is. There you go. Since the square is on both of these, they both get squared.
So you just distribute.
Yeah, it's called power distribution.
Yeah.
Because exponents are based on multiplication, so it plays well with multiplication. Yes?
So on that top equation, it's 1/2 x squared, but then the one below it is 1/4 x squared.
Yeah, we were just on. What am I squaring? What's inside of the parentheses for the square? A 1/2? And what's 1/2 times 1/2?
Yeah.
Yeah. So if I square 1/2, I get 1/4, and if I square x, I get x squared.
Oh.
There you go. Yeah.
That makes sense.
Quick side note. Quick side note. What would you do here?
It's 3x plus 3.
Yeah, you would distribute y, right? Why does it work? Because what are coefficients based on? They are based on addition. And what's happening inside? Addition. So they should play well together. So if I had this, what are exponents based on? What are exponents based on? What operation are exponents based on? If I said what's 7 cubed, do it by hand, what would you start doing?
7.
So, okay, good. So what are exponents based on? What operation? 7 times 7 times 7. Okay, what operation are exponents based on? If I ask you to do this, you told me you would do 7 times 7.
Yeah.
All right, what operation are exponents based on? Multiplication. What's happening inside? Multiplication. So, if for the exact same reason this distributes, this also distributes because I'm cubing the x and I'm cubing the y. I'm tripling the x and I'm tripling the y. You guys with me?
Yeah.
So could I distribute the 3 here? Could I just distribute the 3 here?
No.
Why not?
Because the inside is adding.
Yes, exponents are based on multiplication. It does not play well with addition. I can't just distribute. I have to write this 3 times in FOIL till I go crazy. Okay. That was a good little side note. Where the hell am I hearing? How do I get a by itself? Square root. All right, what's the square root of 3? I don't know. What's the square root of 4? And what's the square root of x squared? Okay, now. We just figured out that a is the square root of 3 over 2 x. Now, I know these sides are gross. I know they're gross. When I ask you to do a sine, you just take whatever the shit this side is, divided by the hypotenuse, correct? The first step is brute force. Just put the shit in there. How would you set up sine of 60 degrees? What would go on top? What is sine the ratio of? What goes on top? The length of which side? What goes in the top to figure out sine? You guys are overthinking it. How'd you figure out sine over here? You put the y piece over the hypotenuse, yes? Okay, what's the y piece in this triangle? It's gross, who cares? What is it? Yeah, go ahead. Square root of 3 over 2 times x, yes? I need you to get over, it looks gross. Whatever it is, the sine requires you to put it on top. So we just do. Well, all right, sine, you're weird. What goes on the bottom? No. Sine. Sine is the y side over hypotenuse, yes? So what goes on the bottom? What happens to the x's? So sine of 60, it's kind of big, but kind of burying the story here. Sine of 60 degrees is the square root of 3 divided by 2. It just is. No, I didn't. Okay. Does somebody have a calculator to borrow? Oh, okay. Real quick, I just want to show you. This is our first concrete thing. If you have your calculator, and Ronnie's like, well, I don't, because you just took it, I'm sorry. Do you guys see right here, sine, cosine, tangent? Don't worry about what's over them, we'll come to it. So if I hit sine, I gotta make sure about one thing. I want to be in degrees. That's all we know right now is degrees. Sine of 60 is this gross decimal, yes? But what did we just say sine of 60 is supposed to be? Yeah, so if I do square root of 3 divided by 2, I got to make sure I come out of the square root symbol, yes? It's the same number. So we just proved that when you have the sine function and you input 60 degrees, it will output square root of 3 over 2. We proved it from this general triangle. What's cosine of 60 degrees? Cosine is going to want the x side, right? Divided by the hypotenuse. So cosine of 60 is 1/2. That kicks ass. That's unexpected. Cosine of 60 is 0.5. Thank you. Maybe. And then I could keep going. I could do tangent, so forth. Yes. The great thing is, once you know these two, you automatically know cosecant and secant. You just have to turn those over, yes? And the funny thing about tangents, let me see if you guys can notice this. There's another way to think about tangent. Since tangent is y over x, let me see if you guys are cool with this. What am I allowed to do to a fraction, to the top and bottom? What am I allowed to do? Multiply or divide. So I am going to be my normal weird-ass self, and I'm going to divide the top and bottom by r. What is y over r in terms of trig? What is y over r? That's sine. And what's x over r? Cosine. So here's the great thing. There are 6 trig functions, yes? You only ever need to memorize 2 of them. Because yes, you do have to memorize sine of 60 is rad 3 over 2 and cosine of 60 is 1. You have to memorize that. I'm going to give you a way to remember it without straight memorization because I hate memorizing shit. So I have so little memorized, thank the gods. So I'm going to try to share with you the way I do it. You can make up your own way you do it. But now, so if I know sine and cosine, I can make tangent. I just divide those two. How do you divide fractions? You multiply by the reciprocal, yes, right? So if I know sine and I know cosine, I have to know tangent. And if I know those 3, can I get the other 3? Flip those. Do you guys start to see what I'm saying? There are 6 trig functions. You have to memorize everything, but you really only have to memorize for sine and cosine because you can build everybody else from those. That's one trick I've done in my life. So I don't have to memorize 6 things worth of inputs and outputs. I just have to memorize 2. Because then I can build. Yes? No, I'm going to let us out. There was one other thing I wanted to do today, but I think that's plenty. I'll let us out of here. So let me know if you have any questions. Otherwise, have a good weekend. Yes?
This whole class just covers all those.
7-2. Yes. 7-1 focuses on angles by themselves. Yeah. So we did 7-2 today. Most of it. There might be a couple we can finish it.
Yeah, what's up?
Are you seeing with corrections? Be this great.